Hello, Brianna. Welcome to Professor Sarah's first lecture video. Today we will be talking about energy and how that relates to the organization of electrons and how to perform electron configuration. So we're going to start with ionization energy. First, it's important to know how to go about the periodic table. So rows are called periods, and columns are called groups. So when we look at the arrows, we can see that it's increasing ionization energy as we go up a group, or it's decreasing as we go down the group. Now, for the period, we see that it's increasing ionization as we go from left to right. So let me just explain that to you, why that is. So let's compare fluorine to iodine. So let me star which atoms. Fluorine to iodine, right? So fluorine has 9 protons. Remember, proton defines the atom. So fluorine, 9 protons. Compared to iodine, which has 33 protons. Now remember, in neutral molecules, protons equals electrons. We're not talking about cations, we're not talking about anions. Those are all charged molecules. Right now we're talking about neutral atoms, molecules, whatever. So if it has 9 protons, in order to be neutral, it has to have 9 electrons. And in order for iodine to be neutral, it has 33 protons, it needs to have 33 electrons. So this is how atoms are organized. We organize electrons into shells. Now, electrons do not orbit the nucleus as if they were rings on a planet. That's not how they work. This is something we have created just to make it easier for us to learn. But electrons in real life are all over the place. So we have several shells. The first shell is the closest to the nucleus. This shell experiences the most positive charge because remember, the nucleus houses protons. And one main concept in chemistry is that opposite charges attract. So we have highly positive charges here. And then you have your first shell, which only can contain 2 electrons, always, only 2 electrons. So let me give you an example of what would go in there. So hydrogen has 1 electron, that would be right here. Helium, 2 electrons, 1, 2. Helium would fill up the complete first shell. And hence why helium is a noble gas, because it has a complete shell. We want all these shells to be complete. That's when they're most stable. That's when they don't want to lose or gain anything. Let me show you why neon is so stable. Neon has 10 protons, so what does that mean? 10 electrons. 1, 2, our first shell is full. Now we see here, second shell can have 8 electrons. So 1, 2 for the first shell, then 3, 4, 5, 6, 7, 8, 9, 10. The first and the second shell are completely filled. That is why it is a noble gas. It fills the shells completely. Alright, and I'm going to show you how you can do electron configuration now. I'm going to piece everything together, so just don't worry. So, like I told you, you only want to really focus on the metals, which are these first two groups. Remember, groups go down. Those are the metals. Metals want to become the previous noble gas because they are most stable. Let me show you to show my my thought process behind that. Let me show you lithium. Lithium, 3 protons, 3 electrons, right? 1, 2, first shell full. 3. That I only have 1 electron in the second shell. I would need 7 more electrons to go to neon, or I could simply lose 1 and become helium. That is why metals always lose electrons, because it's easier to lose 1 electron or 2 electrons in the case of group 2 than gain however many they need to become the noble gas on the right. How the periodic table works is, I don't want to overwhelm you right there. I'm going to clear all this. Right? Clear all this. Okay. So, it's quite simple. You only really care about the metals, like I told you. And you only care about this region for now. I can label this group 1, group 2. Group 1 and group 2 are metals. Group 3, group 4, group 5, group 6, group 7, group 8. That corresponds to each of the groups, right? And you already know that group 8 is noble gases. They are the most stable. And that is because each of these numbers, 1, 2, 3, 4, 5, 6, 7, 8, they correspond to the electrons in the shells. They correspond to these electrons, right? So hydrogen, like I said, 1. Helium, 1, 2. Then you move down to the second shell. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. But here's an easy graph to represent it, or an easy periodic table. So helium is right here. It's 1s2. We call the first one S. The first shell is S. It can hold 2 electrons. This is just, S represents a shape, but I don't really want you to worry about that right now. So all you need to know is the first shell is S, and it can hold 2. That's what this little symbol here stands for. The S shell has two electrons in it, and that's all it can carry. Once you fill up that shell, you have to move on to the next one. So you go to 2s2. So the second shell, so you see 2 right here, it has an S orbital. So shells are made of orbitals. Don't get too caught up in that. Just worry about the first shell can hold 2, the second shell can hold 8. I'm explaining why. The second shell can hold 8 because it has the S orbital, another S orbital just like was in the first shell, and it also has a P orbital. And P orbitals can hold 6. So you have an S that can hold 2 and a P that can hold 6. So that shell as a whole can hold 8. You see the same thing for the third shell. It has 1 S, which can hold 2, and 1 P, which can hold 6. So that's why, that's why the shells beyond number 1 can hold 6, right? Can hold 8. But then we're going to talk about the D shell later, but we're not worried about that right now. So here's the electron configuration table on the actual periodic table. So remember, you have your first shell. This is your first shell. There's only 2 elements because there's only 2 places. So here, let's just draw it real quick. I have the nucleus. It has 1 proton, so it's going to have 1 electron right here. The shell is not full. It's not a noble gas. You have helium. You have 1 electron, 2 electron. That's why helium is a noble gas, because it has a complete outer shell. Every period stands for a shell. That's why you have these numbers. 1, 2, 3, 4, 5, 6, 7. That means first shell, second shell, a third shell, fourth shell, fifth shell, sixth shell. So it's really easy to do electron configuration. I'll show you right now. I just go across, right? So if I wanted to do the electron configuration for nitrogen, I have to go through all of them first. So I go through 1s2 because this shell is completely filled up, right? I just work my way down to nitrogen. So 1s2, the first shell is filled. Because I have 7 electrons, I need to fill the shells until I get 7 electrons. So right now I have 2, so I need 5 more. I need to account for 5 more electrons. Let's go to 2s. 2s2, right here, filled. We're trying to get here. We're trying to get to nitrogen. So that's 4. Then I have my 2p. I have 2p, but I'm only going here. So I only am filling 3 out of the potential 6 that p can hold. So instead of writing 2p6, I write 2p3. And that is 2 plus 2 plus 3 equals 4. All right, let's do another one because I feel like I'm not explaining this that well. Let's do aluminum. So I'm just gonna fill up all my shells first. I need 13 electrons. So 1s2 accounts for this entire top row right here. Then I go to the second row. I see the second row is completely filled because I'm not here yet. So that is 2s2, 2p6, because I'm not where I need to be. I need to trace all the way until I get to aluminum. So I need these, 3s2, but then I'm going to stop at 3p1 because I'm right here. I don't need all of this. It's not 3p6 or 3p4, 3p whatever. I'm right here, 3p1. This would be 3p2 if I went on. Oops, I meant the eraser. I'm not sure if I explained this well enough. If you're still confused, let me know and I can clarify more for you. But just remember, each period represents a shell, and each group represents an electron. So this is 1 electron, 2 electron, 3 electron, 4 electron, 5 electron, 6 electron, 7 electron. So I have to go through completely. Let's say I was at phosphorus, that's 15 electrons. I need to fill up enough shells for 15 electrons. 1s2, it's an s orbital, so it only contains 2. 2s2, it's also an s orbital, so that's only 2. Then I can move on to 2p6, that's 6 electrons. So right now we're at 10. Then I go to 3s2. It's an s orbital, so it only contains 2. Then I go to 3p. Now 3p6, it can hold 6 electrons, but I don't need it to hold that many electrons because I'm right here. I want the electron configuration of phosphorus. So I only need 1, 2, 3. So I would be 3p3. So my electron configuration for phosphorus would be, come on now, 1s2, 2s2, 2p6, 3s2, 3p3. All right, let me know if you need more help.